Hello, today we are going to be going over a quick little introduction on equations, and we're also going to talk about the types of reactions. So you want to be able to identify reactants and products in an equation, calculate the unknown mass based on the law of conservation of mass that we'll be doing, and then also be able to identify the types of reactions by the end of these notes. So first off, to get started, our chemical equations give us symbolic representations of our chemical reactions. So it's going to tell us over on the left here how many reactants we have involved. And then we have the arrow, which then shows those reactions undergo a reaction. And then you produce your products that are written always on the right-hand side. So chemical equations include the substances that are being reacted, which are your reactants, the substances that are being formed, or what is produced, your products. They're also going to be giving you the phases of each of the substances. So you have S, L, and G, which would just simply represent a solid, liquid, or gas. And then you also may see the symbol AQ, which just means that that substance has been mixed in with water. We're also going to have the number of moles of each substance, so how much reactants are needed or how much products are produced, which will be represented by the coefficients. And we'll be doing that in a different lesson where we'll focus on balancing with coefficients. Now, all chemical equations should follow the law of conservation of mass. It states that matter cannot be created or destroyed. Mass, energy, and charge are always conserved. So we're focusing on mass today, but energy and charge as well. We're going to see that there's no change in the total mass in a reaction. The total mass of the products is always equal to the total mass of the reactants. And we're going to use that as our calculation and our template in these next two practice questions. So in these two examples, you're going to be given the equation. You're going to be given the masses of the reactants and products, and then there will be one mass that will be missing. And using the law of conservation of mass, we're going to be able to solve for it. So in this given equation, we have two reactants, and it's producing two products. So I'm going to say that the total mass of those two reactants has to be equal to the total mass of the two products. Okay, that's the idea of this law of conservation of mass. So if we look and read the equation, we have 10.2 grams of magnesium hydroxide. Okay, I'm going to find up here in the equation where magnesium hydroxide is. It's one of my reactants. I can put it in either spot over on the left-hand side, but it has to go on the left. So that's going to be 10.2. It reacts with 18.2 grams of hydrochloric acid, which is HCl. That's also a reactant. So I'm going to put it on the reactant side and put it as 18.9 there. And then it's going to produce 15.2 grams of magnesium chloride, which is one of my products over here. So I'm going to put my 15.2 over on the right-hand side. And now it wants to know, well, what's the mass of water? So I'm going to fill that in as X. So again, I've been given an equation. I've been given the masses of all but one, and I'm going to set them, the reactants, equal to the products. Okay, this is the only calculation for you guys in Regents chemistry where you'll have multiple masses given. Okay, one little thing you should have noticed is even though this HCl had a 2 out in front, I did not do anything with that 2. I just plugged in the masses exactly as they are. So then if we go ahead and solve for this, if I add these two together, you should get 29.1 would be 15.2 plus X. Just like in math, I would then subtract out the 15.2 with the purpose of getting X by itself. So then I'm going to end up with 13.9 grams would be equal to X. So that is the mass of my water that must have been formed from this reaction. So if you want, you can try pausing this next one and try out the question and then check your work. I'm going to go ahead and fill this one in. So I can see in this equation, I have two reactants and they're going to be equal to the total mass of my product. So again, I have two reactants. Their total mass has to be equal to the mass of my two products. Okay, I'm just going to flip over. Okay, I'm going to now go through the question. During an experiment 8.5 grams of hydrogen, and hydrogen is going to be your hydrogen gas right here. So I'm going to fill in 8.5. I then have 15.8 grams of nitrogen, which is my diatomic nitrogen gas. That's going to be this one right here. So I'm going to fill in that 15.8. And then it wants to know, well, how much ammonia is being produced. So I'm going to fill in X there. So my total mass of my two reactants has to be equal to the mass of my product. So when I add these two together, I'm going to get 24.3 grams, which is equal to X. So that's the mass of my missing product in this case. Okay, so one big thing is you're going to have to be able to recognize, based on the information given, that this is a law of conservation of mass calculation, and then be able to properly just set it up and then go through the steps there. The second part of this note is just introducing you to the types of chemical reactions. You're going to have to be able to identify types of reactions as synthesis, decomposition, single replacement, and double replacement. So the first thing we're going to talk about is synthesis reaction. So this is two or more reactants that combine into one product. So you can see here over on the left, we have two reactants, A plus B, and it's making one product, AB. Okay, so they're combining into one. That's a synthesis. Sometimes you'll see it called a combination reaction. So with these three examples over on the right-hand side, you will see multiple reactants. And again, it's going to combine into one product, like in this first one. Same thing. These other ones are two reactants in this case combining into one product. So that is a synthesis reaction. And same thing in this last one. You have two compounds here combining into one compound. So a synthesis reaction. You could also have three reactants that combine into one, as long as it's synthesizing into one product. Okay, our decomposition reaction is just the opposite of our synthesis reaction. We have one reactant that's going to break down into two or more products. So over here on this side, you'll see you have AB, one compound, and it's going to break apart into multiple pieces. So in our examples here, you'll see this first one, we have one product. It's going to break into, in this case, two of its elements. In the second example, same thing, one product breaking into two or more, one reactant breaking into two or more products. And then same thing here, MgCO3. In this case, we have one compound breaking into two compounds. So again, one product breaking into two or more one reactant breaking into two or more products. So you can see synthesis, decomposition are basically the opposite of each other. The other two are a little bit harder sometimes for students to tell the difference between, and that is single replacement reactions and double replacement reactions. So we have single replacement reactions first. We're going to have one element that's going to replace another less reactive element within a compound. So how this looks, if you look over on the left-hand side, is that I have element A and I have compound B, C. So what happens is, if you look from the reactants to products, is that A has come in, okay, and kicked out B. So A is replacing B, where now B it's by itself, and A is now in the new compound. So this is called a single replacement reaction. So in this case, like if we look at the examples, this first one I have Fe, okay, I'm now going to look at my compound where Cu is, and you can see here that Fe comes in and kicks out Cu. So now I have Cu by itself and Fe is in the compound. So one big thing with this structure is that you always have an element plus a compound making a new element by itself and making a new compound in the reaction. Same thing with these other ones. Here I have Mg. It's going to come in and kick out the sodiums. So now sodium is kicked out. So I have my sodium separate. And then Mg is now in the compound. So again, single replacement. In this one, I just want to show you that in this case, because I have a nonmetal diatomic chlorine, it's going to come in and replace bromine in the compound, so the negative ion. So then you have chlorine now in the compound, and then you have Br as your new element. So that's three examples of single replacement reactions. The last one is a double replacement reaction. So this is when two elements are going to exchange places with two separate compounds. And these often form what we call a precipitated solid. So in this one, it looks like the most complicated because you're going to have two compounds instead of an element in a compound, two compounds, okay, which is going to form two new or different compounds. So if we look at where the double replacement comes from, take a look at how we have A, which was with B, but now is with D, is going to come in here and replace C. So A comes in and replaces C, but instead of C getting kicked out by itself, it now comes back to replace A. So they're both of them switch partners. So that's the double replacement part. So over here we have Ag and I have K. Okay, Ag is going to come in, it's going to kick out, but K is going to come back and replace Ag. So they are both replacing each other. So Ag was initially with NO3, it's now with Cl. K was initially with Cl, and now it is with NO3. Okay, see if you can spot the double replacement in this last example. Okay, hopefully you can see here that we have Fe and then K. Okay, Fe was with Br, but now Fe is with PO4, so it switched places, as well as potassium K was with PO4, and now it's with Br. Okay, so you're going to want to be able to have some examples and be able to start to figure out what is the difference between synthesis, decomposition, single replacement, and double replacement reactions so that you can start to identify them yourself.